So we've seen how we can go through and evaluate double integrals, and what does a double integral mean? Well, a double integral can be utilized to find the volume bound by the xy plane and a curve, or some sort of three-dimensional object in space. And so we're going to utilize that concept, and we're also going to approximate that. So you might remember that there was a Riemann sum in calculus. And so if we go back to this idea, let's take a look at just this basic example here where we have a volume that's bound underneath this paraboloid. And one way that we can approximate this is by utilizing the midpoint rule, similar to what you did in Calc 1 or Calc 2. And you can divide it up into different rectangular solids. So you can see in the picture below that what we could do is we could approximate and just go through and say, okay, well, I'm going to divide that up into 4 rectangular solids, and that could be used to approximate the volume. Now there's a lot of underestimation in this example, or at least in this diagram. If we wanted a better approximation, what we would do is we would just go ahead and break it up into maybe 16 or 32 or 64 rectangular solids, but we know that that's pretty much impractical to do by hand. So instead what we do is we just take the limit as those go to infinity. And you might remember the fundamental theorem of calculus suggests that we can go through and just turn that into an integral. Well, in this case, we're going to turn it into a double integral. So what we can do is we can create a double Riemann sum, and from that double Riemann sum, we can go ahead and find the volume by finding the double integral of that. All right, so similar to what you did in Calc 1 or Calc 2, except now it's in 3 dimensions. So we're going to take a look at a couple examples of this. So we're going to start by that paraboloid that we have up there. We're going to use the midpoint rule. We're going to find the exact volume, and then we're going to see what the difference is, if any, between the two. All right, so let's do the really easy part first, the double integral. X goes from 0 to 2, y goes from 0 to 2, the function 1 minus x squared over 4 minus y squared over 9, and then dx dy. In this one, it doesn't really matter the order. This is x, this is y, just because the bounds are the same. However, I would suggest going through and just doing x first and then y next. To evaluate using the midpoint rule, let's consider the xy plane. And we're just going to look at the floor of this. So think of this as like the xy plane. And we want to break this up into 2 different sections. So we have x is at 0 here, and then x goes to 2. Y starts at 0, and then y goes to 2. And so what we're going to do is we're going to break this up into m equals 2 rectangles, and this time, instead of just rectangles that are 2-dimensional, we're going to have 3-dimensional rectangles. So think of this as kind of a rectangle that's doing one of these jobs where it's going in space and it's kind of shooting up from the floor, and the bound of it is going to be the z, or in other words the height of that paraboloid. And so what we're trying to do is we're trying to find the midpoints. Well, we know in between 0 and 2 is 1, and we know in between 0 and 2 is 1. All right, so that helps some. And right here, this point, well, halfway between 0 and 1 in the x direction is a half. Halfway between 0 and 1 in the y direction is also a half. All right, so that's just like our coordinate. And to do that, what I did was I just looked and figured out half of this and half of this distance. Okay, so those are going to be what our ordered pair is. Now, a second example. Next to that, we have this point right here. So halfway between 1 and 2 is 3 halves. Halfway between 0 and 1 is 1 half. Right? And again, what I did was I just looked and I kind of approximated that, or just averaged the distance. Up here, halfway between 0 and 1 is going to be a half. Halfway between 1 and 2 is 3/2. And as you can imagine, the last point is going to be 3/2, 3/2. Halfway between 1 and 2 is 3/2. And halfway between 1 and 2 is 3/2. Alright, so that's how you can kind of break those up into the different rectangles. Now, we need to find the volumes of each of those. Okay, so the volume of any one of those rectangular solids is going to be delta x times delta y times the height. Alright, so delta x is just the change in x, delta y is the change in y, and then the height is going to be the function at the point. So I'm going to call that x n y n. And the good news is that for all the rectangles, the length of the x is 1, the length of the y is 1. All right? And so what we really have is we just have some squares, and then we're going to shoot that up, and that's going to form our rectangular solid. All right, so for the first volume, I'm going to call that V1. We know that delta x is 1, we know that delta y is 1, and we're going to evaluate the function at the first point, 1/2, 1/2. So that's going to be 1 times 1 times 1 minus 1/2 square over 4 minus 1/2 square over 9. And we can stick that in our calculator and compute, and when I do that I get 131 over 144. A second volume, this time we're going to use 3/2, 1/2. So volume 2, that's going to be 1 times 1, which is our length times width, and then our height is going to be 1 minus 3/2 square over 4 minus 1/2 square over 9. And when we compute that, that's going to give us 59 over 144. Right, 2 more times. Our third volume is this 1/2, 3/2. So V3 is going to be 1 times 1 times 1 minus 1/2 square over 4 minus 3/2 square over 9. And when we compute that, that's going to be 11/16. And then finally V4, delta x times delta y, length times width is 1 times 1, 1 minus 3/2 square over 4 minus 3/2 square over 9, and that equates to 3/16. So what's the total approximate volume? Well, that's when we add up all of the different volumes that we just found, V1 plus V2 plus V3 plus V4, and that's going to be 131 over 144 plus 59 over 144 plus 11 over 16 plus 3/16. And the answer I got for that was 79 over 36, or approximately 2.19444. Alright, so we're going to hold on to these values because those are the approximations by the midpoint. So that's our midpoint volume. Now what's the exact volume? Well, what we're going to do is we're going to find the analytic value. So that's going to be 0 to 2, 0 to 2, 1 minus x squared over 4 minus y squared over 9, dx dy. So remember that was our iterated integral that we formulated earlier. If we integrate with respect to x, 0 to 2, x minus x cubed over 12. So add 1, divide by 3, and then 3 times 4 gives us 12, minus just think of y squared over 9 as a constant, so xy squared. And that's going to range from 0 to 2 dy. We're going to substitute 2. The 0 just wipes everything out. So if we substitute 2 back in, 0 to 2 of 2 minus 8/12 minus 2y squared over 9 dy. And 2 minus 8/12, that's going to be 4/3, I believe, because we get 24 minus 8, which is 16/12, which should be 4/3. So let's just rewrite this as 4/3. Now we're going to integrate with respect to y. So that's 4/3 y minus 2y cubed over 27 from 0 to 2. We substitute 2, 0 wipes it out, so we get 8/3 minus 16/27, and then technically minus 0. And if we compute that, if I use my calculator, that's going to wind up being 56/27, or that's approximately 2.07407. Right. And ultimately the question is, how close are we? Well, if we go all the way back, now we got 2.19444. So the midpoint was 2.19444. And then the exact was 2.07407. Alright, so they're reasonably close. I mean, if we wanted to find a percent error, we certainly could. Alright, so let's just go ahead and find the percent error just because we can. So that would be 2.19444 minus 2.07407 divided by 2.07407, and we're going to multiply that by 100% when we're done. So if I shove that into the calculator, I get about 5.80%. Okay, and so not really all that great. All right, but it's not too terrible considering that we only used 4 of those rectangular solids. Obviously, if we used a little bit more, then we could go ahead and try to get a better approximation. All right, so hopefully this gives you a good overview. We're going to take a look at one more of these, so that way we can see how to use this. Next time, I believe it's going to be one of the transcendental types of functions.